right, hey everybody, thanks for coming to our lunch and learn today for SEG. And today we've got Sam Scher with us, and I'm going to let our one of our master students, Ian Campos, go ahead and introduce her. Go ahead.
Hey everyone, and thanks for joining us here on this lunch and learn with Sam Scher. Just to add a bit to the description that you guys got from the advertisement for the lunch and learn. Sam and I are friends and colleagues from McGill University, where she completed her bachelor's and her master's. Her master's was focused on fumarolic activity and mineralization in high sulfidation epithermal deposits, looking at crater lakes at Kawah Ijen in Indonesia, which is an active stratovolcano. And during her time at McGill, she also helped she contributed to a lot of economic geology field trips with her supervisor, Willie Williams-Jones, who you might have heard of. And as the saying goes, you know, the geologists that have seen the most rocks, you know, tend to be the best. And I think Sam is no different from that. During these trips, we're able to go to places like Tanzania, Guatemala, Colombia, look at ore deposits, the fantastic geology worldwide. And I think that kind of contributed to Sam spending several years in Chile, where she worked as a geochemist, and most recently at her current position at Corescan as a business development manager. So in this role, she's been able to contribute to hyperspectral technology and working with other large companies. She recently relocated back to Washington, DC, where she's now, again, looking to promote the business and give more talks like the ones we have today. I think just yesterday she spent some time presenting to the Chilean community, so I think she might welcome being able to present in her native English. So that being said, Sam, please take it away. Very happy for you to be here.
Yeah, thanks, guys. Thanks for having me. And definitely, I think today, my Spanish is definitely rusty, so presenting in English is going to be a little bit easier. Yeah, so again, thanks for having me. I guess what I wanted to do today is definitely inspire everybody to look more, take another look at Skarns. So I'm glad that we have people like Sachin here. Just because when we're working with our different clients that have Skarn, the lowest mineral count that we've seen so far is 35 different minerals in a single Skarn. The most that we've seen is at this point 48, and that's not including subspecies. So there's just so much to learn with this hyperspectral imaging technology that I'm just really here to inspire everybody to take a second look. The other thing though that I wanted to do today is just because I know that there's not much out there in terms of teaching, you know, the basics of hyperspectral. So I know that you guys were interested in learning some of the basics. So I'm going to do a little bit of basic physics, some basics of what, you know, some of the Skarn spectra look like, and then time permitting, I have a few examples. If anybody wants to stay a little bit later, I'm happy to continue onwards, but I think I can get this all handled within about 50 or so minutes. So yeah, if you guys have questions at the end, happy to stay, happy to answer anything. And really, I love giving these talks, so thanks for having me. Well, the trickiest part is always getting this to go to the next slide. Okay. Introduction to Skarns. So I kept this really simple just because I wanted to keep it more in the realm of how Skarns kind of tie in with veneer swer mineralogy, which we'll also chat about in a short while. So Skarns, as you guys probably know, highly variable class of mineral deposits. The best way that I would like to classify them for these purposes is by their economically important mineralization. So iron Skarns, tungsten Skarns, gold, copper, zinc, moly, and tin. There's just so many different ways that Skarns form. Again, I'm going to keep it simple here. Just talking that they can form during regional contact metamorphism in a range of geological settings. Common characteristic, which is what we're going to explore herein, is that you have your calc-silicate mineral assemblages, particularly garnets and pyroxenes. And then you also have the retrograde, which is what happens usually after the prograde assemblage with that calcilicate. And there you're looking at a lot of clays, more silicates as well. And that's also where you start to get your mineralization. Mineralogical zonation patterns, they're pretty well established. And there's been a bunch of papers written over the years, particularly by Maynard, Uende, which has done a great job of mapping these out in the field. A lot of people have done additional petrography, additional SEM work. There's great work out there. But what I'm going to come at you guys is just that with hyperspectral core imaging, there's a lot more now that is literally lighting up, and that we should go back, revisit these Skarns and just see how much more information that we can get out of this. Because when you think about hyperspectral core imaging, the way that I see it is that it's just like having a big thin section that you can see over the continuum of drill holes. So what we're looking at here to our right, hopefully you guys can see my mouse. This is a core photo of just a small section of Skarn. We have these things in Corescan called class maps. And that's just, if you want to think about a class map, that's just a summary map. So like when you make a geology field map, you're going to rank certain lithology over another, and it's going to be a sequence order based on their importance. I'm not going to get too much deeper into it, but just to say that in each pixel, you can have more than one mineral, but we do a ranking system for these summary class maps. So in here, what you're first seeing is in this dark, you see magnetite, and these lighter red colors and pink, there's 2 different sulfides that have been mapped here. And then these maps are just mapping the minerals individually. So you have your sulfide 1, sulfide 2, and a map of magnetite. Quick terminology, I really just put this in here just because, again, the terminology of Scarns, it's just, I mean, for me to work it out, it just took so much time, right? Because there's so many different terms, so many different ways to classify them. I just broke it down really simply for you guys, just so that we're kind of all on the same page in terms of the general classification schemes and terminology. Endoskarns, protolith igneous origin, exoskarns, protolith of sedimentary origin. They'll talk about a dolomitic protoliths, and this will be that magnesian skarn, a limestone protolith, that calcic skarn. Those ones are definitely really important in terms of the mineralogy that you'll be seeing. You also have skarnoids. But again, from that mineral systems point of view, and what I think is just the easier way to focus, and when we're talking about them, would be in terms of their metal association. But of course, just because you have a zinc skarn doesn't mean that you don't have copper and other elements in it. So it just kind of close it out too. Most important thing that I want to say is definitely that Skarn paragenesis. It's complicated. What you'll see with Corescan data is you'll see, for instance, down here in the bottom left, you'll see this is a map of pyroxene, right? You'll have a map of garnet. You'll have a map of carbonate or different types of carbonates. Corescan isn't going to tell you what came first, what came second. That's for you and researchers, for people, the geologists working in the field. That's for us to figure out, right? And the more of these minerals that I see, the more messy that they all look, the more you just really recognize that geology and geologists are super important. The biggest kind of classification schemes as well that I want to just touch on as well is the prograde, which are those distinctive calcilicate assemblages that I'll show some spectra of in a little bit. So you have garnets, you have pyroxenes, elastinite, and others. Your retrograde, that's where you start to see your sulfides and your hydrous mineral phases, epidotes, chlorides, amphiboles, talcs, smectites. But again, just because you have epidote sitting right here in my retrograde assemblage, you can see epidote in the prograde. And all these things, when you see it in this hyperspectral core imaging image, they're all overprinting. You have multiple phases. Again, it's complicated. So geologists, super important. This I modified from McQueen 2005. And what I chose to do here is I chose to include only Vignir-Swer active mineralogy. And so this I've taken from from where the pluton is and moving out towards the host rock of where you're going to find your skarn. And all these minerals that I have here, these being in the pro grade, these are all veneer swirl active, and we can identify them. And then here's examples, some hydrous overprinting minerals, amphiboles, chlorides, epidotes, etc. This is just in general. There's a lot more minerals out there that are in these, and a lot more that we can identify with hyperspectral and hyperspectral core imaging. And then I think the last slide that I have here for my little introduction here is that skarn deposits with hyperspectral imaging. Why am I pushing this so hard? So yeah, we can do detection and mapping. That's what we do. Here's a mineral class map that I have from a skarn in Peru. You're seeing in red, you're seeing some sphalerite, you're seeing some sulfide, iron sulfides in yellow, but then you have these epidotes, chlorides in green, some carbonates in blue. There's a lot going on. We're detecting, we're mapping. However, to do any kind of interpretation here, there's a lot that can be done, whether it's assemblages, whether it's figuring out you have vectors, doing some deposit reconstruction, looking at things from a geomet consideration. These are all things that I'm appealing to you guys to start to work out kind of in this new wave of what's going in Skarn. The clients that we work with have done enormous jobs of different things that we can definitely talk about later that they're doing. And I have some examples of that towards the end of the talk. But again, this is what Corescan and what other core imaging providers do. We identify minerals and point, right? Our interpretation at Corescan is amazing, but this is like, if you think that this is the answer and this is it, any client that I have and every client will say, this is just the beginning. Okay, so an introduction to hyperspectral imaging. Spectroscopy, spectral geology. Spectral geology, it's just a form of mineral analysis. So what you have here, it depends, are we talking about handheld? Are we talking about a core imager? Are we talking about airborne satellite? You have an emitter. So this can be the sun, it can be a light that's producing electromagnetic radiation, which we'll talk about very shortly. Here's a sample. In our case, it'll be a rock. And then you have, so in this case, you're hitting photons against the sample matter. It's either reflecting or absorbing, and anything that's reflected into the spectrometer, once converted, will produce a spectra if there is a mineral that for us at Corescan is active in the veneer or swirl. And you have to understand that certain minerals can absorb at specific wavelengths, and that's why you have this resulting spectra. So really, in order to understand this mineral analysis, you really first have to understand the basic physics of the interaction of electromagnetic energy with their targets, in our case, rocks. Namely, we have to understand what is light and how does light travel from point A, which would be our rock, to point A, sorry, being the emitter, whether it's a light or whether it's the sun. How does it travel from there to there, reflect back? And what does the light do once it gets to point B? And in the end, what you have resulting would be a spectra. This spectra, you have some, I've highlighted some of the absorption features here, 1400, 1900, 2200. I'm not a spectral geologist, but even I know at this point that what we're looking at here is a white mica. They could tell you that, like that. Me, it took me, 4 years to be like, oh yeah, this is a white mica. So, okay. Some terminology that you guys just need to know, because I think you guys probably hear this quite a bit, especially now you start to see more papers out there, more people are talking about it. Handheld has had an amazing run and is doing really amazing stuff in the field and helping people identify mineralogy more real time. And obviously there's been an emergence of the popularity of core imaging. So when you think about what are we looking at, the first thing you'll hear is, talk about the near infrared. So what we see here, we'll start up here in the black. So here, if you can see those little colors, little rainbow colors, these are the things that we can see. We can see things in the RGB, in the visible red, green, blue, and a combination of colors. That's the world that we live in. Right after that, you have the near visible infrared, then you have the shortwave infrared. This is what we're working at when we're working with Corescan, when we're working with handheld. Then there's other systems that will work in the mid-wave or the long wave or the thermal. There's lots of questions that you should be asking your providers in the future. I don't want to get too deep into it, but all I'm going to say is that not every system, if they say that we work in the V near to the long wave, not every system is going to have equally spaced bands or a complete spectrum. And these are all things that are important to consider when you're trying to plan out your program. Are people more concentrated? Is their instrument more concentrated over here? If so, then that's probably good for iron ore deposits. That's what you want, but maybe it's not the best thing for you to do if you're really interested in a lot of clays, where you want more bands, more readings to be concentrated in the short wave. Long wave, there's a lot of chatter out there because it's the only way to identify carbonates. As I'll show you, carbonates can be easily identified in the short wave. Also, people are interested in feldspar detection. So people are very interested in the long wave, but also if things sound easy, they're not actually in many cases that easy. So we can, in the questions and answer section, we can talk more about that. But I just wanted to present that a little bit too, because I get a lot of questions on that. Okay, so let's see how we're doing on time. Good. So infrared reflectance emission spectroscopy, all this is, as we said before, interaction of photons with the material surface. For example, the rock. Light interacts with the or the energy source. This is either reflected or it's absorbed. In the case of the V-near SWIR, there are things about transmitted. I could get into that, but I'm not for the sake of time. But these are things that we're really talking about here when we're talking about how does the Corescan, how does like handheld technology work, airborne as well. And generally what you need to understand about these things for anything that you're doing in the field or things that we're doing here at Corescan, there's no penetration but beyond 3 to 6 microns. So basically what that is to say is that, you know, if we say that we need dry core in order to scan for you, we just need that really top part of the surface dry, and then everything is fine. And also, you know, when people ask, is this a whole rock technique? Well, no, it's a surface technique, right? So whatever you see on the surface and whatever you're pointing a spectrometer at, that's the extent of what you're going to be analyzing. You can't see anything more deep than that. I've done a lot of thinking on what is whole rock and, what is surface and what the differences are. And I think it's pretty philosophical at this point. So it's another topic for another day. 2 key things for you guys to know here. When we're talking about how do you get these spectral plots, there are 2 processes that are important for the V-near SWIR. In the V-near, generally, not just generally, all of the reason why you have absorption features are due to what's called an electronic process. And I'll go into that in the next slide. And in the short wave, you have all of that is controlled by vibrational processes. There's another one called rotational energy, but that doesn't affect here, and it's not applicable. But so I'm just not going to touch on it. But it's really important to understand these fundamental molecular dynamics and the energy states that they're in, because that is just fundamentally how spectroscopy works. This diagram looks really overwhelming. So I'm going to break this down really, in my opinion, very simply. But it's a really important concept to grasp, because it's why spectroscopic measurements are successful in the V-near. The electrons here are going to jump to other energy levels, and this is going to leave a fingerprint behind that's recorded as a spectral absorption feature. So as for chrome, for example, chromium, it has an absorption feature. It has an absorption feature here at 610 because that's exactly because that's recording where the electron gets excited. Iron 3+ here. So, and I should say as well that this over here, this color, this is a magnetite spectrum. This over here is a pimolite spectrum. This is fuchsite, and this over here is hematite. And these are the fundamental areas where these where you have what's called a crystal field absorption feature. And because of this excitement in the electrons, that's why you're seeing these absorption features. In terms of the short wave, incoming radiation, it also causes molecules to vibrate, where the bonds between the atoms bend and stretch in predictable geometries. So here you'll see possible vibrations in the water molecule. So you have symmetric stretches, you have bending, you have asymmetric stretches within this molecule. And actually these are fundamentally how these molecules are moving. And because of these movements, you get these absorption features. Really, a lot of them actually are occurring in the mid and the far infrared of the electromagnetic spectrum. However, and this is kind of, sorry, we're going a little bit, high level here, but in the short wave, you have what's called overtones and a combination of bending and stretching modes that are absorbed here. So when you see kind of all this terminology, these deltas over here that I'm trying to zoom in even with my eyes, these are these combinations and these overtones that you're seeing that are why you can see these absorption features. So over here we have polygorskite in green, we have montmorillonite, saponites, keolinites, and these are all causing this is a process of causing these fundamental absorption features that gives each and every mineral its own fingerprint that we're able to identify. In the end, I think this is a great schematic because what it's showing you here is that you have all of these electronic absorption features up to about, I'm looking here, zooming in, about 1350 or so. And the rest in these vibrational absorption features, 1350 onwards. These are actually what our geologists are mapping. They're mapping, if they're mapping white micas, right? They're mapping these features at 1400, this OH. They're mapping also the 1900 water feature over here. And they're mapping this feature at 2200, this here it is, the ALOH feature. Now, if you have different white micas that have some other substitutions in them, or they have, maybe there's a mixture of minerals in them, maybe you're also seeing a white mica chlorite mixture, then you'll start to see some other things in the spectra as well. But in general, this schematic does a really good job of showing you what exactly our geologists and any spectroscopists in the world are measuring when they're identifying minerals in a spectra. And again, this slide is highly particular, I suppose, to the Corescan method of interpreting data. But I think it's an important one, and I think it's good for me to just speak on behalf of what our geologists do. So when you see a map like this in our data, this is what we call a match image. And what you see over here is in red, this would be close to 100% match over here. Here's our match threshold and our 100% match. Our match minimum that we use is usually 92%. But depending on the mineral, it could be higher. And then, so anything in blue is more towards the threshold. So what does that mean? We use, here's a library spectrum. We're using alunite as an example here. So this would be what we're comparing any alunite to determine whether or not it's alunite or it contains some alunite in a mixture. A high match would be something that corresponds almost perfectly with that reference spectra. Where do we get the reference spectra? We have libraries from the USGS, we have libraries from CSIRO, we have now a large internal library as well, VBHF. So we have a lot of libraries that we use in order to define our spectral matches. So this would be, 100% match to that. And then this one would be, okay, you've hit, some of the features of alunite, the 1480 feature. Maybe it's not exactly perfect, but you've also gotten some other features that are part of the spectra. But this would be more in blue. This would be more of a less match, but we're still saying that it's enough for it to be considered that there is alunite present in this pixel. And the last thing I'll say is that every project that we work on, the reason why it takes so long for the initial, what we call a project library, to be established is because every alunite is different. So if you have an alunite from the El Indio Belt and an alunite from the Maricunga Belt in Chile, they're going to be a little bit different. And so every project needs to have their own, average alunite. Is this me that's writing on there? It's weird. Every alunite for every project is going to be a little bit different. So we also do project-specific library spectrum. Okay, so I threw this in here as just something that's very beautiful to look at to kind of transition us now into talking a little bit more about applications. When we talk about these like very visceral, very, in my opinion, beautiful, but complicated, messy mineral class maps that we put out for these Skarns. So this again is just a summary map of all the minerals that you'll have in your project. This is something that was probably the closest to a pro-grade assemblage that I could find. It contains a combination of garnets, which is in this purplish color. There's some pyroxenes in this darkish yellow, a little bit of wollastonite, light yellow, and then some. This featureless category just means that it has this negative slope that has no discernible absorption features. And actually, from just knowledge of mapping it so often, it's actually the category itself is a combination of anhydrous quartz and anhydrous feldspars. So what potentially this would just be, and these different grays would be some quartz plus or minus feldspars. And it just kind of goes to show that, it's just, this is complicated, this is messy. And this is probably the most pure pro-grade that I could find in all the stuff that we had. Because most of the time when I'm looking at these Scarns, there's just a lot of overprinting, more like what you considered a retrograde Skarn assemblage. All these hydrous minerals, tons and tons of smectite. I don't even know, before people could see this data, I don't even know how they successfully can mine Skarn. Just what a mess in a flotation circuit. Or other kinds of, I'm not sure how everybody in the world mines their Skarns and processes them, but so many different smectites, so many different phyllosilicates. It's just kind of blows the mind, really. So yeah, so this would be a good example of a smectite heavy retrograde assemblage. You have montmorillonite, betallite is more of an iron rich smectite on the spectrum. A little bit of garnet in here, some epidote and chlorite, a little bit of blasting, we have some over here, and a tiny little bit of quartz. When you see quartz, when we name something quartz at Corescan, it means that it has that negative slope, but also it has some water features, potentially because there's some fluid inclusions in them. And that's how we'll identify those. See, is there anything else I want to say about this other than it's messy? Yeah, one thing else that I just want to say is that potentially, I don't have any other images up here, but you see a lot of purple right here. So it seems like there's just a lot of montmorillonite, which there is, but it also could have the same amount of chloride on it. So if you're looking at a Corescan data set, it's really important to have a lot of the different match images up as well, so that you can see the distribution of all of your different minerals. However, also, it's not just limited to, our data sets aren't just limited to images, although really images are data too. There's a lot that people are doing, especially in terms of textural analysis for MET studies that I've seen at other universities. Also, it's something that consultancies are pursuing and companies themselves are using. So images are data, but also all of our data can be exported, is exported in numerical point form. We do it standard at 25 centimeters, but also we can do it at assay interval or whatever interval is of use for whether it's you or as a company. This is an example of what we'll produce. So we do abundances, which are normalized. We'll give all the minerals that you have that sum up to 100%. And then also we'll do, this is an example of something called the Illite Spectral Maturity Index. Basically, it's just the way in which we're able to separate out illites from the white mica group, as well as montmorillonite. And so here, what we'll do besides giving the average value in that interval, we'll also break it down into percentage of montmorillonite, illite montmorillonite, illite, muscovite illite, and muscovite. So, and we'll do that for a lot of times we have chloride, wavelength parameters, we'll have epidotes, we'll have a whole slew of different things. A lot of times it's just what is important to you for your project, and we'll go and we'll work with you and do as many different parameters as you would like. Okay, moving along. So what I've done here is I have about 6 slides where I'm just going to take you through some of the major mineral groupings, really, of minerals that you have in Scarns. And what I just really want to show you guys here is that this is how our geologists at Corescan do the work. These are what the spectra look like. And we've also highlighted here what the absorption features are and what they're tracking in order to map these. In terms of iron sulfides, I have to say that for the most part, sulfides are not diagnostic in the veneer swirl. A lot of times, especially in terms of iron sulfides, a lot of what they're doing is they're using the RGB to map them with color. We have such great resolution in our RGB that this is really how it goes. However, if they're finely disseminated, it's usually kind of a no-go. So for each project, it's a bit different. And a lot of times the best we can give you with sulfides is just more of a kind of a best estimate that we can. It's never going to be, 100%. However, though, you have some minerals like sphalerite, which are interesting because it actually does have a mappable feature in the shortwave. It has a unique spectral profile. It also has, because sphalerite tends to have a little bit of an iron component, so it also will have an absorption feature, an iron absorption feature. Molybdenum actually has mappable moly features. So those ones are kind of the odd ones out, if you will, in terms of sulfide mapping. But then, when it comes to things like chalcopyrite, pyrrhotite, those ones just, it's more project dependent, and especially considering if they're continuous, if they're larger grains. To the left here, I have a picture of sphalerite. You can see its distribution in the core, and you can see how we've mapped it pretty well here in the map, the image match. Other ore mineralogy and skarns, I've just chosen a few here. There are lots of different carbonates, oxides, a wide range of silicates that are mappable. I've chosen here to highlight magnetite. So obviously for iron skarns, it has this broad feature around 1050, an iron 3+ feature. Malachite, it's carbonate, so you can map it using the 23, what we consider the 2340 feature. But then also it has a little bit of a copper feature associated with it that we can map as well in the veneer, excuse me. Sauconite, I'd never heard of before a few years ago when we started mapping it extensively in a skarn in Mexico. But sauconite is really interesting because now we just see it really everywhere, especially in these zinc skarns. And so it's a zinc smectite, which, I mean, messy. And then hemimorphite, that's just another one that we see not so much in abundance, but we see quite a bit through zinc skarns as well. This over here is a picture of malachite distribution within a skarn. Portal to skarn mineralogy, I've chosen here just to highlight carbonates. There's always a lot of questions about, not so much questions, there's lots of, for me, I get these, a lot of what I would call almost accusations, like, oh, well, you can't map carbonates in the shortwave. And it's like, well, actually you can very successfully. I just wanted to pull this up. Obviously carbonates are going to be very ubiquitous in Skarn, it being one of the typical host rocks. And not only can we map carbonates consistently, but also there's a lot of information that we can get from carbonates from this 2340 feature, which is the most diagnostic feature that they have. And the shifts in there are gonna, in the wavelength shift, will show you whether you have calcites or dolomites. What's that other one? I'm blanking. But anyway, it will show you a whole range of different carbonate species that you can have. But in addition to that, because we also have the veneer, and all of our spectrometers are co-registered, meaning that we don't have problems with being able to identify. Very simply put, we don't have problems with the combination of the veneer and the swirl in our interpretation. But here, these are big iron features, right? So here we can identify iron carbonates, no big deal. Here's where the manganese feature is in the shortwave. So this would be, this spectra over here is a mixture of a manganese and an iron rich carbonate. So there's actually a lot of utility that we have for identifying and mapping carbonates. So here you have just a plain carbonate map. And then here we're mapping some of the shifts in the carbonate composition. So you can tell if you have something that's more dolomitic, more calcitic, something's approaching a rhodochrosite, siderite. So it's pretty fun stuff. Calc-silicate mineralogy, I have put a stacked plot over here, again, to highlight some of the mineralogy that we're looking at. These are grossular and almandine, two different types of garnets. And then I have here diopside, orthopyroxene, hemimorphite. These, I'll say, are not, because you're relying almost solely on the veneer and their absorption features with iron. If there's a lot of mixtures, especially because of all the retrograde mineralogy where you start getting a lot of water features, it's not straightforward or as simple as saying, no big deal, we're mapping garnets, we're mapping pyroxene everywhere. These ones, yes, we can do, we have been very successful in certain projects in mapping, but if you have a lot of overprinting, just because you can see a perfect garnet with your eye doesn't necessarily mean that you can map it. But again, I have seen a lot of beautiful garnet and pyroxene mapping. where all veneer square systems will excel would be definitely in the short wave with all their much, they're very beautiful diagnostic absorption features. These are just examples of a lot of the different minerals that we're mapping throughout a range of skarn. So we have, talc, vesuvianite, apophyllite, biotite, chlorites, amphiboles, epidotes, serpentine, and also you're looking at a range of compositions in them. The prehnite is also interesting as well, and I have a little example of that coming up. Over here, just looking at a straight up map of where you have epidote, where you have chlorites, and also here I've chosen to put the epidote wavelength feature, so looking at increase in iron and increase it towards an increase in aluminum, so more of like a clinososite over here versus an epidote. And then here's the wavelength feature for chlorite. Depending on the project you're in, you're usually either using the 2250 or the 2350 wavelength feature, and that you're just mapping the magnesium to iron shift. The last one I wanted to bring up, it's just the variability in chemistry, particularly like what we see with smectites, but there's a lot of minerals where we can look at the chemistry of them, and it makes it really interesting to start talking about things from, talking about any kind of metasomatism that we're seeing, even, whether, we're starting in an iron-rich skarn or calcium-rich skarn or magnesium-rich skarn, what are we looking at? So over here, these are 5 different smectites, and they all are charismatic, and they can all be told apart, which if you were to grab this rock in the field, for me, I mean, sure, grab my scratcher and it could say, okay, for sure, there's a clay component here, but how much deeper than clay can you just go here? But with having something like the availability of an instrument like this, not only are you saying, okay, at this point, we definitely have sapphonite. Because it's an imaging system, you can also, because you have so many pixels and you're able to find M-member species for them, you can really start to pull apart all the different subspecies that you have and run that through your entire drill holes to see all this incredible information and the texture. All right, so let's see the time. All right, so we've kind of, looks like we got about 15 minutes left. So maybe I'll do one case study, talking a bit more about MET, and then maybe we'll do some questions. Let's do this one. This one's something that's really underappreciated in imaging, is that we do incredible work with blast hole samples. I have taken this case study from Johnson et al. 2019. I recommend it for everybody to read. They did some really, it's really impressive. They did some really basic stuff and they pushed it a really long way. Some of the stuff definitely was a bit more complicated, but it just really goes to show the utility of how you can apply relatively simple methods to achieve something that's just a really elegant solution for a lot of things. So it was definitely more of a MET study. Basically, they were looking at, in our mine, we have a really big recovery problem. But the first, so I have 2 examples from this paper that I wanted to highlight. The first is just this extreme diversity of mineralogy that you can see using core imaging systems. So this was using a different system. In the Corescan system, in a standard chip cell tray, we see about 1,500 pixels. And so what, I also think about, because we have a lot of studies like this with our clients. And so what's important to remember is ultimately what's being mined, processed, and milled are minerals. So not just having, your gold, your copper, your zinc, whatever the element of interest is, or some of your deleterious and penalty elements, it's really important to understand both what the mineralogy is going in, and also particularly starting to understand maybe what are your deleterious minerals. So one of the first very simple things that they did was they were like, okay, the outputs that we currently have from our geologists in the field that are looking at these blast hole data is they're able to say, okay, in this green polygon, we have Skarn. In this brown polygon, this is a little bit more abstract, but this brown polygon, we have biotite hornfelds. This light green one, we have calc-silicate hornfels. And over here in pink, we have a supergene phyllosilicate polygon. And that was all the information that the METs had going into the mill. By looking at the hyperspectral data, and so what they did was I think that their sample here was, I think they had about 300 samples. And what they're able to do was taking these 300 samples, they did some kriging. But what they were able to see was that, okay, so here's actinolite, chlorite, biotite, muscovite, illite, and kaolinite. So what they were able to see was just a general pattern of where their mineralogy was hanging out. And so that already, particularly to me, because I've seen some studies like this internally, it already adds value, whether you're talking about vectoring, whether you're talking about to mill. You can already start to think about, especially if you have something like illite, there's different properties of illite that make it potentially difficult for your processing circuit. Same with chlorite. There's just, everything has its own story, right? So understanding where these minerals are is important. And the second thing that they did was that they noticed that in their mine, the biggest problem that they had, and this is the Phoenix mine in Nevada, the biggest problem that they had, the most problematic mineral was talc, where even small concentrations, that less than 1%, could cause major overfrothing, requiring significant cleanup and costs, decreasing sulfide recovery, and increasing entrainment in the concentrate. So talc is extremely fine-grained in this deposit, and I've always seen it to be fine-grained in a lot of the other deposits that we've worked with. And really understanding its location was critical to them. So using hyperspectral core imaging, they were able to identify areas where they had higher talc percentages. And also in these very small polygons, maybe it's difficult for you guys to see, these are the areas where they knew that they were having problems with, where they were having a lot of these overfrothing in the mill. Now seeing that there's some additional areas where they could potentially have problems. So it's really helped the METs to create a threshold for acceptable volumes of talc and to identify maybe where those are. And I just want to say, for when you guys are reading this paper, just because of the system that they were using, they had some trouble mapping out the talc itself, but talc to any spectroscopist that you're talking to has a very distinctive signature. And at Corescan, we map it with ease. So here's a talc spectrum for everybody. Okay, so I think I'm going to stop there. You guys can definitely have this, so you can look through some of the other examples that I had. But I guess what I want to do now that we have 10 minutes left is just to ask if anybody had any questions.
You have a question.
Yeah.
So in terms of identifying sulfides and silicates, has there been any approaches to trying to incorporate Raman spectroscopy into your systems? Because that would certainly help you be able to do that. And there's a nice database already of Raman spectra in the rough database. Yes,
that's a great question. So at Corescan, what we decided to do was to finish our Corescan 4 rollout, which was basically finer. I always forget if it's lower or higher, but basically increase the resolution of the Vernier and Tour spectrometers that we already have. On the side, though, we are working on Raman development that we're going to be incorporating into our machine. The most important thing that you have to know about Corescan is that all of our spectrometers, as well as our RGB and our laser profiling system, are all completely co-registered. And so then it's not just a matter of just tagging on a Raman to the back of it and just kind of running a Frankenstein machine. So like the development pipeline for us is a bit slow in that sense. But yes, we are interested in that. And that is something that we've been in development for a while now.
Very
Great
cool.
question.
Thank you.
Yeah.
Great. Thanks, Sam. Looks like we've got a few questions in the chat that I can go ahead and read out.
Sure.
The first one is from Lewis. He asks, how refined has the technology become insofar as changing back and forth between different wavelength sources? And then he expands a little bit and says, insofar as these tools measure the sample's, quote, skin, what are the most important surface character pitfalls and the strategies that can be used to adequately prepare core and non-core samples?
Okay, so I think I'm going to take this. Okay, I think I'm going to take this in sections, and then Lewis, if you want to keep following up with me, we can probably work this out. So at Corescan, we use quartz halogen bulbs. So consistent light, zero problems. But you know, for if you're doing an airborne survey, right? Obviously you have to, not obviously, excuse me, everybody, but you would have to be, you know, out there when there's no clouds in the sky, right? So all the systems, every system is going to be different, but we have at Corescan, and we've always had a consistent light source that has a perfect Planck curve. So in terms of illumination, we are good. What was his next part of the question? I forgot.
Can you hear me okay?
Yeah.
Hi, I was had to do with the fact that the tool measures doesn't measure very deeply into the sample. So my question is, what are the most important surface character pitfalls, if you will, that you might encounter, and what are the strategies that you can use to adequately prepare core and or non-core samples for these tools?
Gotcha. Oh no, did we lose? I got really excited in scrolling here. Hold on. Okay, so I'm going to say actually the hardest thing for us to measure is perfectly flat oil core, because it has less imperfections for the photons to reflect back off of. That said, whole core, split core, hand samples, chips, cuttings, blast holes, I mean, whatever, soils, whatever you want to send us, no problem. And the other thing for that, that I think answers your question is that the top part of that core has to be dry. Otherwise, we're going to get water features in the spectra. So as long as that top 6 microns or so is dry, then it's not a big deal. And then in terms of if you're doing, say, chips, cuttings, blast holes, or soils, it's going to be a question of, and you probably want to, for each study, you want to probably try out a few different things. Do you want to wash it? Do you want to sieve it? Do you want to do one where we're looking at fines, where we're looking at more of the coarser parts of it? It's really going to come down to what you want to focus on your study. If we're doing something for a mine site though, right? For that, we found that not washing them and just kind of scanning as is best. If anything, you know, shaking them up to try and, you know, not only be analyzing the very fine fraction was better, but also because of electrostatic properties, you'll always get some of the fines that are attached to the coarser particles. So it's kind of just a matter of trial and error in that, and really thinking about the study. But for us, in terms of how the machine reads it, the only thing I wouldn't recommend you guys send in be pulps, just because when it gets that fine, our spectrometer resolution is 500 micron in the HDI 3, and it's 250 micron for the spectrometer in the HDI 4. So if you think about pulps, they're just so fine that you're going to get a lot of mineral mixing. So yeah, we can identify if you have chloride or if you have, you have white micas, but we're not going to be able to really get into the meat of it and really start separating it out nicely and saying that you have, you have phengite and paragonite and muscovite. Like a lot of that stuff kind of comes out in the wash. You're going to be able to identify magnetite when you have some other iron bearing minerals in there. Probably not, just because it's just so mixed. So really, if you just kind of stay away from pulps, everything else we do a pretty good job of.
Thank you.
Welcome.
All right, we've got another question in the chat from Tim. He asks, when discussing the percent match of the sample spectra to reference spectra, is it peak picking or matching, or do you compare every nanometer?
Okay. Yeah. Let's head back there. Much more of a visual person. Yeah, so in our like full short course, there's much more information on this. We have so the secret sauce of Corescan, of course, like the instrumentation is the best. I'm not even biased about this, but really the secret sauce is our spectral geos and the software that we have that was coded in-house. And so what this software does, it allows our spectral geologists to say that, so we have obviously the general, alunite spectra, but it also allows to say that, okay, in the project spectrum, we also have this shoulder over here, or we have this slope over here. And actually it's not, the average one actually isn't centered at 1480, it's at 1482. Like it allows for things to be changed and allows for things to be weighted. So it is true, it is absorption feature matching, but it's also slopes, it's also shoulders, it's also a range of things that our spectral geologists are saying that this is important, this is important, this is important. So yeah, there you go. There's the secret of Corescan.
Can I follow up real quick?
Yeah.
Yeah, I was just gonna say, so how do you calculate a percent match? Because you said you had like a threshold of like 90 something percent, 92%. How do you actually calculate that percentage?
So that I would need to get to answer that like perfectly. I would definitely need to get the man that coded our software involved in that. But actually, when you talk about, how do you get that? Our software, once you have set that an alunite in this project looks like this, and you say that I want the threshold to be 95% match or better, our spectral geologists at the beginning are going through, more or less pixel by pixel and really, tightening things up. And as they go through more core, tightening things up and refining it further, it's iterative. But what's really doing this and bringing it through, because, in a meter of core, we have 200,000 pixels. And in the new HDI4 system, we'll have 800,000 pixels. So obviously over an entire, drill hole of 500 meters, a kilometer, 2 kilometers, like it's impossible. One person cannot do all that. So what we actually do in our software is it's an algorithm that's pulling all this through. So once we set that threshold, that 95% or better is what this is going to be, or 92% at the minimum or better is what this is going to be, it's actually controlled by said algorithm. As to how that is built, that is beyond my capacity to answer.
Okay, thank you.
Yeah.
I might just sneak in here and ask my question. You talked
Hopefully
about
it's a softball.
Yeah.
No kidding.
You talked about, obviously alteration minerals are very hard to identify in the hand sample or drill core. And you talked about the metallurgical, value in having sort of at least a broad idea for the bulk composition of different mineral assemblages and that sort of thing. At what point of a project do you think benefits most or presents greatest value from bringing in hyperspectral imaging, at the exploration phase or sort of the development phase. Could you comment on that?
Yeah, so I'll say first that it's never too late. But that said, I think the most inspiring story that I have, and that is now being adopted by major companies. We've been working with this company called Regulus Resources in Peru since 2017, and they're a junior based on the TSX. They have a project, I think I just said it, the Antiquary project. And their whole vision is that they want to make sure that when they go to sell a project, that there are no secrets, that there is just, everybody is understanding of what the downstream effects are of their deposit. Their deposit's very complicated. It's a high sulfidation, skarn, and porphyry overprints. It's the whole shebang. But the philosophy of being able to plan ahead so that when they present this, and they presented it to many investors already, but as they present this project, it's just that they know that in order to develop this or to develop that, that they already have all this information and they've kind of worked it out already, so that when they go to say that, all right, we're ready to sell, everybody's just aware of it. So I really like that idea of starting early. You know, you do your geochemistry in the early stages too, right? And so for that, you know, I think what we do right now is we put a large emphasis on, we have, you know, 5 grams per ton gold here. We have, you know, 1% copper over, you know, 200 meters. Yeah, that's amazing. But at the same time, what if you're 1% copper over 200 meters? What if it is intermingled with porphyry or something else, right? Like that could be potentially a problem for a met circuit. And so now you have, you know, companies that will buy and sell projects, and I've seen projects where, you know, they had to shelve a very large investment because of the fact that they had so many different intermingled clays. They actually had some intermingled arsenic around pyrograins. It was a complete mess. But they didn't know that before. So I think it's just kind of, in a philosophical sense, it's also just about, it's about having more honesty in the industry, but then also just being able to prepare. Like if you're just delivering to geomets at the beginning, that, you know, or mets, process engineers, you're just delivering to them something that's very general and very schematic, that's not going to be really helpful towards them doing anything. Also, when it comes to selecting, you know, test work samples, if you're just saying that, okay, here I have, you know, Skarn 1, Skarn 2, Skarn 3, but what if Skarn 1 and Skarn 3 are actually very similar? Or what if you actually have 5 different types of Skarn? So being able to, I did a talk on domaining for geomet test work sampling a few months ago at a Chile Explorer conference. And that was all about using the hyperspectral, not just the point data, but also the imagery data, and getting using whether it's neural networks or a different methodology, but taking information from the images themselves as well as the point data to domain this stuff so that you can sample sample things better, whether you're interested in comminution or interested in flotation. So I think starting early is great, but if you have to start later because of limitations on, you've been operating mine for 100 years. I mean, you just have to work on from a small, you know, work in, you know, a pilot study area, and then kind of move up from there. And if this pilot study is working for you, then maybe you start to integrate into more and more of your model. I've seen this too. So, and we're in the process of working with a company right now where they're, you know, piloting their new model, which has now incorporated our data. So it's never too late, but better to start early, my opinion.
So we have 2 more questions and then we'll wrap things up. One is a pretty simple one. So someone is just asking how many Corescans are in the US right now, and will one be in Denver anytime soon?
The closest one right now is in Hermosillo, so right over the border. I recommend that one. right now, we don't have any quick plans to be in the US unless there's somebody that really wants to work with us. We have 4 new Corescan units coming into play in May. So if anybody's on the phone still that is interested, we have some homes for some of them, but we also have room. So for us, we can mobilize units anywhere. We have the capacity to build more if there's big projects anywhere. We don't have any plans right now to be in the US, but we could be in the US
Cool.
if somebody was interested.
So then the last question, it's a combination of Stephen and Jashan's questions that they have in the chat here, but basically they're just asking how often is this technique compared with more traditional methods like traditional petrography or newer methods like automated mineralogy or general SEM mapping, and in terms of like quality control, how is it compared to those methods?
Yeah, so comparisons are, I think I would rather, instead of talking about comparisons, I'd rather actually ignore that and talk about integration of the methods, because every method is telling you is adding knowledge in a different way. So one of the examples I have here is from the Skarn in Brazil. And this study, what they did, so I have the name here, they Mesquita et al., 2019. And what they did was they combined petrography with, they actually used point data here, so handheld SWIR with SEM, and just general geochemistry as well. And what they were looking at was they had found with their SEM and their petrography work that Pranaya was around some of their gold grains. There was bismuth around there as well. And so what they were able to do using their geochemistry, using their shortwave data, their hyperspectral data, was they were able to basically make an index of which they could apply for targeting. So I think when you're talking about comparing techniques, one for one, I think that I know that that's never going to work because everything's giving you a different piece of the story. So it's really about how are you going to combine them for something that's more holistic, because you really just have to first have a question. And then once you have that question, then it's about trying to figure out how you go about answering that question. And I think that this study did a really good job of showing you that it's not just one method, it's a sum of parts.
Well, so I'm going to push back a little there, because in terms of identifying clays, I mean, the gold standard would be XRD, which is obviously a bit more time consuming, but it gives you it gives you the best answer. So I would be interested to see how Corescan and that data compare to really high quality quantitative XRD. And I'm sure it's very close, but I would just be curious to see how it compares.
So I'll push back on you too.
Fair enough.
Yeah, no. So I think when you're talking about XRD versus a method like Corescan, the question there is more of what is composite and what is surface, and how those things talk to each other. But then an XRD actually, right now, it's still considered more of a gold standard, but it actually doesn't do such a good job of identifying clay minerals. If you've ever seen that anhydrous, the amorphous class that they put as a readout, the amorphous class in an XRD, even if you're doing clay separations, that's just kind of a bundle of different clay minerals that they couldn't identify. And an XRD as well, I think when you do it kind of in this like a large commercial sense, I think people take for granted that it's giving you all the answers and they've built a beautiful library. So when you talk about it in an academic system, I think it's also much different than when you get commercially. It's only as good as the person analyzing the data. And I've been very disappointed recently looking at, kind of these more commercial interpretations. But I would argue strongly that the gold standard for clay mineral identification is actually hyperspectral. Definitely in terms of other minerals, the XRD is a better shot, but also with them, it's never going to give you a 1-for-1. It's really understanding the 2 data sets, 3 if you're using anything else, and just trying to figure out. It's a complicated question. I've seen a bunch of
Yeah.
studies.
Yeah, Sam, I'd like to follow up with this because some of the minerals like white mica, it has clear and sharp absorption features, 1400, 1900, 2200, 2250, 2350. And those ones, when you go to match in the library, that'll be much easier to identify those. But if you look at other minerals like garnet, pyroxene, or sulfides, and you look at the spectrum, they're pretty broad. It doesn't have really a clear absorption feature like a peak or trough. In that case, how much uncertainty is involved in those mineral identification?
That's a really good question. Yeah, so I guess when you have, I think there's two parts to this question. So because the Corescan system has so many pixels, we're able to get really good end member species. So that's really helpful for us in terms of when our algorithm goes through and being able to pick apart and identify, you know, okay, if it has these absorptions, then it's certainly, this is definitely, there's a Grossulite in this mixture. But you're absolutely correct. Like if you have something like this, these really broad absorption features or something like what you can see that in this orthopyroxene.
Yeah, like the Hemimorphite, almost nothing.
Exactly. But even when you have this, if you have a mixture with it, with other iron bearing minerals, yeah, you're absolutely right that, you know, there is a very large chance that the signal can get swamped out. And that's why there is a trickiness to it. I think, Xiaoshan, though, if you want a much better answer than what I'm giving you, definitely, you know, chat with Cass and Carrie about it. But and if anybody has more like these kind of spectral ones, if you are interested, our spectral geos are definitely the resource that you want to go to. But that's a really good point, and you're correct.
Thanks.
All right, well, if there's no other burning questions for Sam, I'll go ahead and stop the recording and let's do that.